today. So 4-7 continued. Okay, here's another example. A poster is to be rectangular and contain 240 square inches of printing. It must have a 1-inch margin on both sides and a 2-inch margin on the top and bottom. What outer dimensions would minimize the area of the paper? Okay, so a poster, as in like that periodic table of the elements up on the board there, some sort of poster that's going to be a rectangle. All right, this won't be anything like that huge. It's only going to contain 240 square inches of print. So for example, it could be 24 by 10, the printed part. That in addition to the printed part, it must have 1-inch margins on the side and 2-inch margins on the top and bottom. Now, given those restrictions, how should you design it? How should you set up the poster so that it uses as little paper as possible? I mean, you could go to some ridiculous extremes. You could design a poster that looked like this, couldn't you? With a tiny strip of printing in the middle, like that. I suspect that would use too much paper, right? You could go to the other extreme and make it really skinny vertically. But probably somewhere in the middle between those crazy extremes is the optimal, right? So that's what we're being assigned to do, is figure out where is the best choice if you're going to use as little paper as possible. And I think we can already kind of predict what's going to have to happen. I mean, after all, we have this difference in margins, right? We have 2-inch margins top and bottom, 1-inch margins on the side. What, if you're going to use less paper, would you like to make smaller? The 2-inch margins or the 1-inch margins? You'd like to make the top and bottom margins smaller because they're the 2-inch margins, right? And 2-inch margins, that's just blank paper. You'd like to use as little of that 2-inch margin territory as possible. So what's that going to influence in terms of the dimensions of the poster? So you would, in terms of height, you'd think that the height would be greater than the width, because the width is what controls the length of the top and bottom margins, isn't it? And you want those to be shorter, and so to make up for that, you'll have to make it taller, so you still have the same amount of printing in there. So that's just a loose gut feeling of what's going to happen. That doesn't tell you exactly how to do it. We need to nail down exactly how to do it. And so we get started. We draw a picture. We attach some variable names here. We get going with that stuff. So let's draw a picture. So here we go. Here's our poster. And I'm going to put my margins in. I'll put my 2-inch margins top and bottom and my 1-inch margins on the sides. So 2-inch margin across the top, an equal 2-inch margin across the bottom, and a 1-inch margin down the side, and an equal 1-inch margin down the other side. Okay, so there's my margins, and within those, that's where my printed text is going to go, or my graphics, or whatever. That's where, this is all empty white space around the edges, but here's where my printing goes, right, and whatever. It's all like that. There's the poster. There's the poster's message. Okay? Now, what do we know about that blue tagged stuff in there? What did they tell us? 240. That's 240 square inches of actual content that's in there. So this part in here, I'm going to tag. This is 240 square inches. I'm also going to tag up my margins now. We already said what they are. This is 2 inches. This is 2 inches. Whereas this is 1 inch. And this is also 1 inch. Everyone getting it now? That's the description that we've been given. Something like that. Any questions so far? Okay, and we want to do this in such a way that we use as little paper as possible. All right, so we want to minimize. So what we got control over here is the dimensions. We could make it tall and skinny, we could make it really wide and short, or we could make it somewhere in between. But we've got control over that, and that's what we need to set up as our variables. So what is it that varies depending on how we design it? What varies is the width and the height. Okay? There's 2 ways you can tag those. You could tag the width and the height to be the width of the whole paper and the height of the whole paper. That's fine. Or you could tag it to be the width of the printing and the height of the printing. I've done it both ways. I tend to favor the second option because it makes the constraint relatively easy to write down. If I tag this as x and this as y, the constraint is simply x times y equals 240. Is that right? But if I tag the whole width as x and the whole height as y, my constraint gets pretty ugly. It ends up saying x minus 2 times y minus 4 equals 240. I mean, it's legitimate, but it's harder. So I think I'm going to go with labeling the inner dimensions as x and y rather than the outer dimensions as x and y. As I said, you can do it either way. It doesn't really change the answer, but I think it's a little less cluttered if we do it the second way I just described. Okay, so I'm going to tag it the way I just described. I'm going to call this x, this inner dimension, x, and this inner dimension, y. Are we okay with that? And so I can write down my constraint now. My constraint is this requirement about text amount. The text area is 240. So my constraint here is that x times y has to be 240. And as we know, usually when we have a constraint like that, we're going to end up wanting to solve that for either x or y at some point, both of which are pretty easy to solve for. They wouldn't have been so easy in the other format that we described. Could have done it, but it would have been a bit uglier. Okay, so that's the constraint. We must obey that. Now let's pay our attention to the thing we're trying to optimize. Remember what that is? Minimize the area of the paper. So now we do have to add those margins in to get the paper area. Because how do you get the area of a rectangle? Length times width. So we're going to need to know those, and we don't have those tagged right now. We've got the inner guys tagged, but that's not the area of the rectangle. That's the area of the printing. So let's throw the net a little wider here. That is how long? X plus 2. Everyone agree with that? It's x plus a 1-inch margin on both ends. That's a total of x plus 2, isn't it? And then vertically, similar logic, that's y plus 4 because of those 2-inch margins on the top and bottom. Everybody making sense of this? So that's the thing we're trying to minimize, the product of those two. We're going to multiply them together. So minimize the area of the paper, I'll call it A, which is its width, x plus 2, times its height, which is y plus 4. Minimize the total area of the paper. Okay, and as we've had with the farmer's corral or the farmer's field or whatever you want to call it, we have a constraint here. We have a function here with too many variables in it. We've got x's and y's. We've run into that a couple of times now where we had too many variables, and we've used we had it same with the tin can. We had too many variables, R and H. We only wanted one of them. Didn't have it with the oil rig though, did we? Because we only had one variable there, so we didn't have to worry about that one so much. But a lot of the time you do have the too many variables problem, and that's when the constraint can help you. So I either want to get rid of the x and keep it all y's, or get rid of the y and keep it all x's. Doesn't really matter which. I guess we're more used to working with x's, aren't we? So I guess I'll do that. So what is y in terms of x? Yeah, it's 240 over x. So wherever I see a y, it's legitimate to replace it by 240 over x from the constraint. This making sense? Okay, so I get that the area is x plus 2 multiplied by 240 over x plus 4. So that's the function. Now, in terms of restrictions on x, what's the size restriction on x?
It can't be smaller than 2.
X can't be smaller than 2? No, I don't think there's even that restriction.
Oh, just
You could make x like microscopic, right? I think the only thing you couldn't make x is as small as 0, because if it were literally 0, you wouldn't equal 240. You've got to be a hair bigger than 0 is about the only restriction we have to obey. There's no upper limit on x. X could be 100 miles long. Of course, what would y end up being as a result? Incredibly tiny, right? It would really, because we only need that area still only needs to be 240. So if you make x enormous, you have to compensate by making y really, really small. But there is no theoretical upper limit on the size of x. So our only restriction here, x has to be positive. It can't be 0, but it can be any positive number. So that means we won't be able to do it by that closed interval method, the one where you check the endpoints. We don't have endpoints. So we're going to have to use either the first derivative test or the second derivative test. Probably the second is what we'll opt for. I almost never use the first. I did on the oil rig because I didn't like the idea of taking another derivative of that ugly mess. They usually aren't that ugly though. This one won't be. I'll multiply this out next so I don't have to use the product rule, kind of avoiding the product rule that way. And then I'll take the derivative, then I'll find the critical values, then I'll test them, and then I'll make my conclusion. Everyone okay with the plan? For most of you, from past experience, the hard part is over. For most people, the hard part is not the calculus. It's the model. It's setting it up. It's interpreting it. It's coming up with your labels and changing them into a formula. That's the hard part. And actually finding the max or min, for most people, that's the easy part. So let's get multiplying this out. Let's expand it. And we get that A is 240 plus 4x plus 480 over x plus 8. Is that right? If you use FOIL on that? Obviously the 240 and the 8 go together and make 248. I'll write that on the end. And since I'm going to be taking a derivative in a second, I'll write this 480 over x as 480x to the negative 1. It makes the derivative easier to take. So the area of the paper is 4x plus 480x to the negative 1 plus 248. Okay? Now let's crank the derivative out. So a prime, it's a pretty easy one, is 4 minus 480x to the negative 2. You okay with that? Critical values. Those are places where the derivative is 0 or undefined. Now I will write this derivative as a fraction. In other words, I'm going to rewrite it with the x on the bottom again. So that means that 4 minus 4 over x squared has to be 0. Take the 480 over x squared to the other side. 4 is equal to 480 divided by x squared. Clear the fraction by multiplying through by x squared. 4x squared is equal to 480. Divide through by 4. Okay? So x squared is equal to 120. Everyone okay with the arithmetic here, or the algebra here? So x is plus or minus the square root of 120, but we have this restriction that x must be positive. So I'll throw out the minus. X is the square root of 120. Now 120 is divisible by 4. I don't think that anything larger that's a square goes into it though, does it? If you take 4 out, it leaves 30. 30 doesn't have any squares. 30 is 2 times 3 times 5. There's no squares there. So that's the best you can do. You can rewrite this as 2 square root of 30. If you take a 4 out. 4 on the outside becomes a 2, of course. Okay, so that's our critical value, 2 root 30. It's probably exactly what we need. It's probably the minimum, but we need to test it. So how do we test it? As I said, almost always we'll use the second derivative test. Let's get that second derivative figured out. Oh, one just quick comment. What about the other kind of critical value? The undefined kind? There's your derivative. Is it ever undefined? Yeah, at 0. But x has to be greater than 0, so that we don't worry about that one. Okay? It's not in our domain. This is the only critical value in our domain. Okay, a double prime. Crank it out, and we get 960 x to the negative 3, or 960 over x cubed. Okay, there's our second derivative. Now we use the second derivative test, which means we take the second derivative and plug into it the critical value in question, the one we've just found. We want to know if it's a max or a min. Maybe it's neither. We plug that into the second derivative, so we get 960 over 2 square root of 30 cubed. Now, thankfully, we don't really care what the answer is. We care about what about the answer? The sign, exactly. And clearly, what sign is this? Yeah, it's positive. That's all we care about. Don't need to work that out. Just need to know it's positive. Which means it's concave up, which means it's a min, which is good for us because that's what we were trying to find. We were trying to find the min. Any questions so far? So that's it. We pretty much solved the problem. We do need to do a little bit of finishing here. We need to know what y is, right, which you can get from right here. And not quite the end, because remember, x and y weren't the question. It didn't say what's the dimensions of the printed area, which is what we've just found. It asks what are the dimensions of the outer, in other words, the paper itself. So what do I have to do to my x and y answers once I've got them? Yeah, I need to add my margins in. I need to add 4 inches of margins to the vertical and 2 inches of margins to the horizontal, don't I? To get the final answers for the paper. So we're pretty much done with the hard part. It's just a bit of bookkeeping now, but we're almost done. Okay, so let's find y. Y is 240 over x. So y is 240 over 2 root 30. So y is 120 over root 30. We could rationalize that by multiplying top and bottom both by root 30. And so we get that y is 120 root 30 divided by 30. And then the 30 divides into the 120 4 times. You okay with that? So y is 4 root 30. Okay? So it's kind of going the way we predicted. Look at those two in comparison with each other. We found that x was 2 root 30 and y is 4 root 30. Now remember, y is the vertical. So it's ending up, the printed area is ending up being twice as tall as it is wide. Didn't we say we would think it would be taller? Because we want the big margins, the 2-inch margins, to be on the shorter sides, which means that we need them to be, you know, on the narrow side, which is the x side. That's exactly what we're seeing. Okay, final answers. The paper should be, let's do the width first. It should be 2 root 30 plus 2 inches wide and 4 root 30 plus 4 inches tall. Is that right? Where did the plus 2 and the plus 4 come from? Adding the margins back in. Right? We found the blue area, x and y. We need to add these green margins onto them. Okay? We also had them there too, if you like. Plus 2 and plus 4. Those were the 2 dimensions of the paper, not just the print. Any questions about that? Okay. Let's do a different problem. All right, so let's do a more of a financial problem this time. Okay. A small orchard will yield, I'm just making, I have no clue if these are even close to the right numbers, will yield 80 apples per tree if it is planted with 16 trees. For each additional tree beyond 16, the yield per tree of the whole orchard by 1 apple. How many trees should be planted to maximize the orchard's total yield? Just made those numbers up on the spot. We're probably going to get some ugliness as a result of that. Usually when I write with these for exams, problems like this, I work it out so things work out as nice whole numbers and stuff like that. So I wouldn't be surprised at all here if we end up predicting a fractional number of trees. So we'll round to the nearest whole tree if that happens. Okay. So everyone understands the basic idea is if you overplant a region with a crop, what tends to happen to the yield per plant? It decreases because they're kind of struggling for the resources from the soil. In the case of an orchard, they're also struggling to get enough light as the other trees around them tend to shade them out, that kind of thing. So, it's, as I said, it's a small orchard. It's only, they're basing it on 16 trees. If they put 17 trees in, they're all struggling a bit more to get their yield up. So as a result, instead of producing 80 apples per tree, they'll only produce what? 79 apples per tree. And if you put 18 trees in, they'd only produce 78 apples per tree, etc. Does that make sense? Okay. But you get a whole new tree. So even though you lost 1 apple per tree, right? 1 apple per tree on 16 trees only loses you 16 apples. Right, actually 17, because you've got your 17th tree as well. But that 17th tree is also going to produce how many apples? It's also going to produce 79 apples. You're still to the good, aren't you? So yeah, you definitely want to plant 17 trees at the very least. maybe 18. So you try it again. I've actually had people on an exam do this by trial and error. I shouldn't say trial and error. It's not error. It's very organized. They'll say, I'll try 17. Okay, here's the answer. I'll try 18. Here's the answer. I'll try 19. Until they hit, and then they'll start to go down again. They'll say, oh, this is the one. And so it'll say very explicitly on the exam, you must use calculus to do this problem. You do not do it just by trying things until you hit the sweet spot. Got to use calculus to do the problem. So let's set it up. Now, this is a variety of problem that you see quite frequently. It's not always trees. Other ways I've seen it, a hotel can rent out all of its rooms if it only charges $60 per room per night. If for every $5 they charge beyond that, they lose one room rental. They have this many rooms, that kind of thing. It's the same kind of thing. It's this tension between increasing one thing decreases the other. In that case, increasing the rent per room decreases the number of rooms they rent. But that's still not necessarily bad. Having one empty room, say you had 200 rooms, one empty room, but you charge $5 extra for all the others, you're still better off, right? Same kind of deal as the orchard. I set up once where, of course, it was a very Delta-centric problem. We had the old paddle steamer, the Queen of the Delta, and you could rent it for so much, but for every passenger you put on extra, they charged all the other passengers $1 less, that kind of thing. And so how many passengers should you get on there to maximize the profit for the company, that kind of thing. They're all the same kind of problem. Now, you had a question.
Yeah, is 96 minus x times x going to be our formula?
I'm not sure. I haven't even thought about it yet. Maybe. Sounds about right. It will certainly be a little product like that. It depends on what you're going to choose x to be. So maybe you should tell me what you've chosen x to be.
Trees.
Is x the total trees of the orchard, or is it the trees beyond the base number 16?
I used it for both. I added, because we have 16 trees to start off with and 80, so each time you go more than that,
Okay.
then you lose a tree. So I added 80 and 16 to be 96 minus x. If it was 16, then it would be 80. If it was 17, it would be 79.
Okay.
So then multiply it by x.
Maybe pursue it. See where that leads to. I'm not going to do it that way myself, but it's not saying that you're wrong. It may be a good way to do it as well. What I've found to usually be the easiest way to set these up, whether it's the hotel problem, the Apple problem, or the Queen of the Delta paddle steamer rental, whatever, I've found it to be easiest to let x, because x can represent a lot of different things in these problems, let x be the additional number of. So in other words, in this case, it'd be the number of trees I plant above the base number 16. It's usually easier to do that than to let x represent total trees. You can do it that way as well, but I usually find let x be the number of extra trees rather than the total trees. It usually works out simpler, and logically it's easier to set it up. So let's do that. Let's let x equal the number of extra trees beyond 16. Okay? And we will only have one variable in this problem, and that's the variable x. Okay, now what we're trying to maximize here is the total yield of the orchard, which I'm going to call y. Okay? So I'll write it down in words first. What's the total yield of the orchard? It's a very basic, intuitive thing. It's the number of trees multiplied by the number of apples from each tree. Does that make sense? Okay? It's just the number of trees in the orchard multiplied by the number of apples per tree. So at the beginning, before we started messing with it, it would have been 16 trees multiplied by 80 apples per tree, right? That would have been the base amount. But now we're going to start putting extra trees in, apparently. And so that's going to start varying somewhat. Let's now convert this into symbols. So I'm going to call this yield. I'll call it y. Y for yield. Y is the number of trees. Now, we had 16 trees, and we're going to add to them how many more? x. That's a variable. We don't know exactly how many that's going to end up being, but we'll call it x. So it's 16 plus x. That's the number of trees we're planting. And then that's multiplied by the number of apples per tree. Well, it was 80, but we have to reduce that yield by 1 apple. Is that what it said? Yeah, 1 apple for every tree extra. So it'd be 1x. Now, I don't always go with 1 apple. Sometimes I go with 2 apples. So that would have been 2x, or whatever. Exactly. Does that make sense? So 16 plus x plus times 80 minus x. That's the yield of the whole orchard. And before I take any derivatives, I think I'll multiply that out. Somebody help me out here. What is 16 times 80? I'm not good at arithmetic here.
1,280.
Thank you. 1,280. 1280 minus 16x plus 80x. That will be plus, what's 16 from 80? 64? 64x, and then minus x squared. So there is my yield from the orchard. What about a domain for the function now that we've got the function? What's the domain? Well, what's x? X is the number of extra trees. Okay, so what's a sensible domain for x to be? Well, there is actually nothing to stop you planting less than 16 trees. Theoretically, you could. So how much less could you go? You could go back as far as 16 from where you're currently at, because that would reduce you to 0. So x has to be no smaller than negative 16, because then you'd run as negative trees. You can't plant negative trees, right? But you can reduce the number you already have by up to 16. So I think here our domain is that x has to be greater than or equal to negative 16. If you went with negative 16, you would have reduced the orchard down to having no trees at all. You can't go less than that. Does that make sense? You can certainly go as much beyond that in theory, mathematically in theory, as you like. You can plant 1 million trees in the orchard. Well, you can plant the seeds anyway. They'd never grow. But anyway, theoretically, you can go bigger and bigger and bigger. But you can't go smaller than having no trees. So negative 16 would be where you'd hit no trees, wouldn't it? 16 plus x is the number of trees. So put a negative 16 in there, you'd be down to having 0 trees. Does that make sense? So remember, x is not the number of trees. X is the number of trees beyond 16. So, all right. Okay, so there we go. Now we need to maximize it. So we take its derivative, find the critical values, test them, etc. This will be an easy one. I mean, it's a parabola. It's not going to, its second derivative is just going to be a constant. It's going to be a super easy actual math thing here. The hard part's now behind us. So what's y prime? 64 minus 2x. Is that right? So what's the critical value? There'll only be one. It's where y prime is 0. 64 minus 2x is 0. X is 32. You have a critical value at 32. Okay. We need to test it. What's y double prime? Negative 2. Therefore, if we use the second derivative test, what's y double prime if we plug 32 into it? Well, this y double prime is so incredibly boring, it doesn't care what you plug into it. What do you always get out? Negative 2. Okay, it doesn't care what you plug into it. It's a constant. So negative 2, that's negative, so it's concave down, so it's a max, which is what we expected. After all, we can all see this is an upside down parabola. It's not going to be a min, is it? We found that the peak of the parabola is at 32. That's what we've just found. Okay, and that's our max. All right, now that we've found the max, let's make sure we can answer the question. What did they ask again? How was it worded? How many trees should be planted to maximize the orchard's total yield? Well, we had 16 already, and we're going to plant how many extra, apparently? 32 extra trees. So that'll be a total of 48. Hey, it worked out to be a whole number. Kind of lucky, I guess, because I did make the problem up at random. But so 48 trees total. Okay. So to answer the question, they need to plant a total of 48 trees. And in case you're reading this later and you wonder where that came from, it's the original 16 plus the 32 extra trees that we just figured out X needs to be. Does that make sense to everybody? So we can triple the size of the original plan. We can really pack them in quite densely. It pays off. What would the yield per tree be down to, however, by that time? 80 minus 32. Yeah, so 48 apples per tree. We could have gotten 80 out of each tree if we'd given them some space, but it still pays us more to overcrowd them and get it down to only 48 apples per tree, because the additional trees more than make up for that reduction per tree. Any questions about that? Okay, we have like 13 minutes left, and we don't have enough time to finish a problem, but I think we can get through the hard part. I'll go through a setting up of a problem, which we won't be able to finish. Okay, so example, a new Walmart is going to have 200,000 square feet of floor space. Okay, so we're going to be designing its dimensions. Now we're going to go very basic. The roof, well, Walmarts usually are pretty basic. The roof and the floor, they're going to be 200,000 square feet regardless of how we design it. We could design it to be a narrow corridor 3 feet wide and a mile long, which would be silly, but it wouldn't change the floor space, would it? Or the roof space. So we'd pretty much pay the same for both the roof and the floor, regardless of the dimensions. So we're going to ignore the roof and the floor in the design, because they wouldn't matter. The area of them would not change, because we're going to obey. This is essentially our constraint. But what we're going to have going on here is the usual typical deal with most big box stores. It's going to have a glass front, which is going to be expensive, and it's going to have, what do they call those kind of blocks? Cement block sides, anyway. Cinder blocks, concrete blocks, whatever, for the other 3 sides. And those are relatively cheap. And we're going to design it in such a way that we optimize the cost of construction based purely on those walls. Because we've already agreed that the roof and the floor, same cost regardless, because we're going to have to stay with the 200 square feet of that. Okay, so a new Walmart is going to have 200,000 square feet of floor space. It's a rectangle with a glass front wall costing $150 per linear foot, whereas the other 3 walls are cinder block and only cost $50 per linear foot. Again, I have no clue what construction costs really are. I'm just making numbers up, okay, at random here. Those may be way low or way high for all I know. $50 per linear foot, by the way, this is implying that 10 feet high wall, that 1 foot width is going to cost you $50 from floor to ceiling. Okay, when it says linear foot, that's what I mean by linear foot. Or the glass at the front, one foot width of the glass from floor to ceiling costs you how much? $150 from floor to ceiling. That's what we mean by linear foot. Okay, you can imagine what the question is going to be. What dimensions should you design it to be? In other words, how wide should it be? How long should it be? It's a rectangle. What dimensions would minimize cost? So ignoring all other considerations. So you don't need to start worrying about the roof or the floor or the doors or the windows or any of that kind of stuff. Ignoring everything else, what dimensions minimize construction cost? Okay. So it's an easy problem to visualize because it's just a rectangle. So here's my rectangle. There's my cinder block walls. And then I have a glass wall at the front, which I'll make a different color. Here we go. There's the glass wall at the front. All right. And I've already kind of made an assumption there in the basic picture. I'm already assuming the glass wall is going to be shorter because it's more expensive. And because of that, the opposing cinder block wall at the back must be the same length. It's a rectangle, so it also will be shorter. Whereas the two side cinder block walls will tend to be longer because they're cheaper. So you can get up your area that way more cheaply. But we want to know precisely how long should they both be. So how many dimensions do we have to keep track of here? 2. We'll call them X and Y. Okay? And we already have a constraint. It was told us right away. What constraint do we have? The area, in other words, X times Y, has to be 200,000. Does that make sense to everybody? X times Y, it says it has to have 200,000 square feet of floor space. So we have that constraint. This is glass here, and the others are the 3 cinder block sides. The constraint is X, Y equals 200,000. We're not minimizing that, we're just obeying that. Now, the thing we minimize is the cost. So we need to minimize, and since it's cost, I'll call it C. And C comes in 2 parts. The glass and the cinder block. Okay? So how much am I going to be paying to build that glass wall? 150 times every foot. And how many feet is it? X feet. So it's going to cost me 150 X. Does that make sense? Okay, plus. And then I pay $50 a foot for the cinder walls. So that's 50 times, and how much cinder block wall do I have?
2y plus x.
Yeah, 2y plus x. Everyone see that? The 2 sides are both cinder block. There's 2 y's and an x. The side opposite the glass wall is an x, isn't it? Everyone okay with this? All right, too many variables again. Let me clean that up a little bit first, though. Let's distribute it out and combine like terms. And if I do that, I get a 150, and then there's another 50, isn't there? So that's 200x plus 100y. Okay? That's the formula, but it's got too many variables. So what do? I replace one of them by its x equivalent or its y equivalent. That's the constraint coming in. Solve the constraint for either one. It doesn't really matter. We tend to prefer working with x's because we're used to it. So let me solve this for y so I can replace y with an x formula. Question?
Why would it be 2y if we're saying that the 3 other walls are going to be cinder block?
Well, this is the cinder. This is all cinder block, and $50 per cinder block foot. 2y. So remember that's y. It's x, right? 2 y's. The black ones are the cinder blocks, so 2 y's and an x. Y plus x, all cinder. Okay, so solve this, solve it for y. Y is 200,000 divided by x. Then I can put that in here in place of the y. Okay, so I get c is 200x plus 100 times 200,000 divided by x. Okay. So C is, I can't even see it from here.
100x plus 20 million.
Okay, thank you. 200x plus 20 million. And I'll write it as x to the negative 1, because I need to take its derivative, don't I? Okay. Now, in terms of a domain, how small or large can x get to be? And again, I think it's one of those basic ones. The only restriction on x here, mathematically, is it has to be positive. It can't be 0, because you would disobey the constraint if it was 0. But just a tiny bit positive would be enough. It would be ridiculous if you let x be like an inch. Can you imagine building a Walmart an inch wide? It wouldn't make any sense, but theoretically it could be. So that's our only restriction, that x has to be greater than 0. Okay, so derivative, it's an easy one. It's 200 minus 20 million x to the negative 2. Critical values, you'd set c prime to be 0, so you'd set this formula to be 0. By the way, I'll change it back to a fraction at this point. I'll restore this to the denominator. That has to be 0. We'll take this to the other side, and we'll get 200 is equal to 20 million divided by x squared. We'll multiply both sides by x squared. So 200x squared equals 20 million. We'll divide both sides by 200. And we'll go that x squared is, I need to knock 2 zeros off of this and divide by 2, so I'll get 1. If I take a couple of zeros out, I'll get 100,000. Is that right? And take the square root of that. So x is plus or minus the square root of 100,000. The negative is not in our domain, so we would discard it. So x is 10 million is a square, isn't it? 10 million is a square of 100. So I can take 10 million out. Sorry, not 10 million. 10,000. I can take 10,000 out as a 100. And what does it leave behind if I take 10,000 out? It leaves us a single 10 behind, doesn't it? So it's 100 root 10. That's our critical value. What do we now need to do with it? Test it. The second derivative here is pretty easy. That goes to 0. This becomes positive 40 million x to the negative 3, doesn't it? So a double prime is 40 million. X to the negative 3 means divided by x cubed. I'm really rushing here because I'm out of time. So what would you do with this to test it? You plug it in here. Would it be positive or negative when you plug it in? Positive, right? Positive means concave up, which means it's a min, which is good. We were trying to minimize cost. We've minimized it. So that's how x needs to be. And then finally, you'd go find y. And the formula's right there. That's y, isn't it? So what would you put in here for the x?
100 root 10.
Yeah, 100 root 10. You probably want to rationalize it, get the root 10 out of the bottom, but that would give you your y. Any questions about this now? I'm sure you can finish this on your own. I'm not going to come back on Monday and finish it. I'll leave you to, just takes another 5 minutes and you're done. Okay?